lesson, we're going to look at how to use the unit circle and special angles in special triangles to get exact values for trig ratios where the angles are given to us in radians. Before we can evaluate things like this, tan of 11 pi over 6 or sine of 5 pi over 6 and get exact values for those, I need to remind you about a few things. I need to remind you about your special triangles, your unit circle, the cast rule, what a reference angle is, and of course, SOHCAHTOA, the foundation of trigonometry. So let's review all of those things, and then we'll evaluate some trig ratios. So I'll go over this quickly because I'm assuming all of this stuff is a review for you. SOHCAHTOA, you would have learned about that in your grade 10 math class, and you know that's just an acronym that tells you about ratios of pairs of sides in a right triangle. So if we have a right triangle with a reference angle theta, if you see sine of that reference angle, you know that word sine tells you that from that reference angle, what we're looking at is the ratio of the opposite side over the hypotenuse. Hence, so. If you see cosine of a reference angle, you know that means that from that reference angle, you're looking at the ratio of the adjacent side to the hypotenuse. And if you see tan of an angle, you know that means from that angle, we're looking at the ratio of opposite over adjacent. Hence, TOA. And why is this useful? Well, let's read over here. If we know a right angle triangle has an angle of theta, all other right triangles with that same angle of theta are similar. And what do we know about similar triangles? We know they have equivalent ratios of corresponding sides. So if we have a right triangle with a reference angle of, let's say, 20, all other right triangles with that same angle of 20 are going to have the exact same sine, cos, and tan ratios. And let me show you that in this demonstration here. Okay, so in this application, I have it calculating the sine, cos, and tan ratios from this reference angle 40 right here in this right angle triangle. So it has them being calculated. The sine ratio of 40 is 0.64, cos ratio of 40 is 0.77, and tan ratio of 40 equals 0.84. Now, if I change that reference angle of 40, watch all these ratios are going to change. Right, let's change it to our reference angle being 30. Notice the sine, cos, and tan ratios changed. But if I create a new right triangle but keep that angle of 30 the same, I know that triangle is going to be similar to this triangle, meaning all these ratios are going to stay the same, right? Similar triangles have the exact same shape but are just different sizes. So let me keep that angle of 30 the same and keep it as a right triangle, and watch what happens to these ratios. The ratios all stay exactly the same as I change the size of this triangle but keeping it shaped the same. The side lengths are changing, but the ratios are staying constant. So I know that sine of 30 in any right triangle, doesn't matter its size, I know it's always going to be 0.5 because it's going to be similar to every other right triangle that has that angle of 30. Okay, so now that you have a reminder about similar triangles and SOHCAHTOA, let's remember reference angles. So hopefully you remember the terminology principal angle or standard angle and its reference angle. So any angle over 90 has a reference angle. The reference angle is between 0 and 90, always. Your reference angle is always going to be between 0 and 90. And it helps us determine the exact trig ratios when we're given an angle over 90 degrees. The reference angle is always the angle between the terminal arm and the closest x-axis. And I've given you 4 diagrams over here on the right. These represent the 4 scenarios. If your terminal arm, which is this arm there, is in quadrant 1, the principal angle, which is the angle between the positive x-axis counterclockwise to the terminal arm, that's going to be equal to the reference angle, which is the angle from the closest x-axis to the terminal arm. They're equal in quadrant 1. If our terminal arm is in quadrant 2, theta, the principal angle, would be that angle right there. Beta would be the reference angle, which is the angle between the closest x-axis, which happens to be here, and the reference angle. So it would be this angle inside here. And hopefully you can see in the next 2 diagrams as well, the reference angle is always the angle between the terminal arm and the closest x-axis. So in there and in here. And the principal angle is always the angle between the positive x-axis all the way around to the terminal arm. So once again, let me open a GeoGebra application just to demonstrate this further to you. So notice the principal angle is always going to be the angle from the positive x-axis to the terminal arm. So if I rotate 130 degrees, that means from the positive x-axis all the way over to the terminal arm, that's a 130 degree rotation. Now that 130 degrees has a reference angle of 50 because the angle between the closest x-axis, which would be a 180 degree rotation, and the terminal arm would be 50 degrees, right? The difference between 180 and 130 is 50. And I'll just keep rotating around so you can see the relationship in the other quadrants as well. The red angle is the reference angle, the blue angle is the principal angle. Blue angle is always from positive x to the terminal arm, and the red angle is always the angle between the terminal arm and the closest x-axis. Now let's talk about the cast rule, but before I talk to you in depth about the cast rule, you need to understand the unit circle. The unit circle is going to be key to you actually having a full understanding of trigonometry. So here I've drawn a unit circle. A unit circle is a circle with a radius of 1. That's why it's called a unit circle. So how is this unit circle, the circle with the radius 1, helpful? Well, if I have a terminal arm that rotates some angle of theta, if I can figure out the x and y coordinate of where that terminal arm intersects the unit circle, so if I can figure out the x and y coordinate of that point, I actually will know the cosine and the sine ratio for that angle of rotation. Why is the x coordinate equal to the cosine ratio of theta, and why is the y coordinate equal to the sine ratio of theta? Well, if I were to create this right triangle inside the unit circle, to get to this point xy, I would have to travel x units that way and y units that way. That's why I'm able to label those side lengths x and y. And because this circle has a radius of 1, I'm able to label this side length 1. And then if we know SOHCAHTOA from a reference angle, if I were to evaluate sine of this angle, sine of theta equals opposite over hypotenuse, y over 1. So I could say sine of theta equals y over 1, and y divided by 1 is just y. That's why I'm able to say that the y coordinate equals the sine ratio. And how about if I did cosine from this angle? Cosine of theta would equal adjacent over hypotenuse. So cosine theta would equal x over 1, which is just x. That's why I'm able to say that the x coordinate is equal to the cosine ratio of theta. So understanding that the y coordinate of where we intersect the unit circle is equal to the sine ratio of the angle, and the x coordinate of where we intersect the unit circle is equal to the cosine ratio of the angle is going to be foundational to us understanding not only the cast rule, but also understanding why we're able to write equivalent trig expressions later on in this lesson. Okay, now let's go back up to the cast rule and see why the cast rule actually makes sense based on this unit circle. What is the cast rule? It says when finding trig ratios of positive angles, we are rotating counterclockwise from 0 degrees towards 360. So that just means we're rotating from this positive x-axis counterclockwise back to 360. So we're going in that direction. The cast rule helps us determine which trig ratios are positive in each quadrant. So when you write cast rule, you write it in this order, C, A, S, T. And in quadrant number 1, we see the letter A. That means all trig ratios are positive there. In quadrant number 2, we see an S. That means that only sine is positive in that quadrant. Cos and tan would have negative ratios. Quadrant number 3, we see a T. That means tan is positive, which by default then means sine and cos are negative. And in quadrant number 4, we see a C, which means cosine is positive, which means sine and tan are negative. So for each ratio, sine, cos, and tan, there are 2 quadrants where they're positive. Let's look at sine. Sine would be positive in the all quadrant, of course, and in this quadrant. So it would be positive in quadrant 1 and 2. Why? Well, we know the sine ratio is equal to the y coordinate where we intersect the unit circle. And where are y coordinates positive? They're positive above the x-axis. So in quadrant number 1 and quadrant number 2. Where are y coordinates negative? Below the x-axis in quadrant 3 and 4. That's why sine is positive in 1 and 2, but negative in 3 and 4, because y coordinates are positive in 1 and 2, but negative in 3 and 4. And then cosine, well, that's positive in the all quadrant and in the cosine quadrant, so quadrant 1 and 4. Notice those are the 2 quadrants where x coordinates are positive. And we know that the cosine ratio is equal to the x coordinate. So hopefully you're making that connection between the x and y coordinates and why the cast rule is able to tell us why each ratio is positive in the quadrant it says. And also know that tan is equal to sine over cos. So if we do the quotient of the y and the x coordinates, that tells us tan. And that's why tan is positive there and there. Because in quadrant 1, x and y are both positive. In quadrant 3, x and y are both negative. And a positive divided by a positive or a negative divided by a negative are both positive. That's why tan is positive in quadrant 1 and 3. All right, so you now remember SOHCAHTOA, the unit circle, cast rule, and reference angles. The last thing I need to remind you about are the special triangles. So we have the isosceles special triangle, which I have in red here. And since it's a right isosceles triangle, I know that both of these angles are 45 degrees, which in radians is pi over 4. So I can label both those pi over 4. And since both of those angles are pi over 4, I know that these two side lengths have to be equal, so we call them both 1. And then Pythagorean theorem would tell you that this side is root 2. This half equilateral triangle, it has a right angle, and since it's a half equilateral, I know that this angle would be 60 degrees, which is pi over 3 radians. And this angle up here is half of 60 degrees, which is 30 degrees, which is pi over 6 radians. And then this was a 2 by 2 by 2 equilateral, so this side is 2, this side is half of 2, and then this side using Pythagorean theorem would be root 3. So these are my two special triangles. Because I was able to get exact side lengths for each side, I could find the exact value of sine, cos, or tan of pi over 4, pi over 6, or pi over 3. All right, let's go on to actually figuring out some ratios. Let's start with tan of 11 pi over 6. So I need to, first of all, when I do these questions, draw a Cartesian grid and then label the x and y axes with the angles of rotation. So we always start at the positive x-axis and we rotate 0 radians. And then go counterclockwise, 90 degrees, which is pi over 2 radians. Another 90 degrees brings us to 180 degrees, which in this course we label as pi radians. Down to 270 degrees, which is 3 pi over 2 radians. And all the way back to where we started, that's a full 2 pi radians, so 0 or 2 pi. Those are coterminal. Since I want the tan ratio of 11 pi over 6, what I need to do is draw a terminal arm that has rotated 11 pi over 6 radians. That's really close to 2 pi. It's close to 12 pi over 6. Let me draw it. So when we rotate, we always go counterclockwise. So I need to go 11 pi over 6. So that would be a rotation all the way around to about here. And since the principal angle is 11 pi over 6, I like to label the tip of the terminal arm with that angle, so 11 pi over 6. And now if I want the tan ratio for 11 pi over 6, what I can do is use its reference angle to help me figure out what that ratio is. So what's the reference angle for 11 pi over 6? Remember, the reference angle is always the angle between the terminal arm and the closest x-axis, so it would be the angle in here. And we always call that angle beta. So beta is going to represent our reference angle. If I want to figure out beta, I need to find the angle between the closest x-axis and the terminal arm. So what's that angle? Well, the closest x-axis is 2 pi, and the angle is 11 pi over 6, so let's find the difference between 2 pi and 11 pi over 6. Now, you wouldn't always have to write this, but I can do a little calculation off to the side. Beta would equal 2 pi minus 11 pi over 6. I'll get a common denominator. I'll rewrite 2 pi as 12 pi over 6. So I have 12 pi over 6 minus 11 pi over 6. That's 1 pi over 6. So my beta is pi over 6. Now, why is this important? Well, I can use this reference angle to help me get the ratio for tan of 11 pi over 6, as long as I remember to consult the cast rule. Let me label the cast rule, C-A-S-T. So I'm in the cosine quadrant. What does that tell me? That tells me in this quadrant, only cosine ratios are positive. So when I'm evaluating, so here's my actual work. When I'm evaluating tan of 11 pi over 6, I'm allowed to get that ratio by doing tan of its reference angle. So tan of 1 pi over 6. As long as I remember to make this ratio negative, because I know in quadrant number 4, only cosine is positive, which means the tan ratio has to be negative. So tan of 11 pi over 6 is equal to negative tan pi over 6. And what's tan of pi over 6? Well, remember our special triangle. Tan of pi over 6, well, here's a pi over 6 reference angle. Tan means opposite over. So tan of pi over 6 is 1 over root 3. That means negative tan pi over 6 is negative 1 over root 3. And we could rationalize the denominator. Multiply top and bottom of this by root 3 to get that root 3 out of the denominator, and we would get negative root 3 over, well, root 3 times root 3 is root 9, which is just 3. So tan of 11 pi over 6 equals negative root 3 over 3. Let's try another one, sine of 5 pi over 6. Let's always start by drawing our Cartesian grid and labeling the angles. 5 pi over 6, well, that's less than 1 pi. Right, that's less than 6 pi over 6, so it's before pi, but it's greater than half a pi, So I know this is going to be in quadrant 2, and often it helps people if they rewrite these angles on the x and y axes with the same denominator that you see in your principal angle. So pi over 2, we could rewrite that as 3 pi over 6. And pi, you could think of that as 6 pi over 6. So we can clearly see that 5 pi over 6 is between 3 pi over 6 and 5 pi over 6. So that means my terminal arm starts at the positive x-axis and rotates to around here. I'll label the tip of this terminal arm with its principal angle, 5 pi over 6. And to find sine of 5 pi over 6, I'm going to need to know the reference angle that goes with the principal angle of 5 pi over 6. Remember, the reference angle is the angle between the terminal arm and the closest x-axis. So I need the angle between those two highlighted sides, and I will call that angle beta. And beta is going to be the difference between 6 pi over 6 and 5 pi over 6, which is 1 pi over 6. So my reference angle is pi over 6. And how can I use that reference angle to help me figure out the ratio for sine of 5 pi over 6? Well, let me label my cast rule, C-A-S-T. Notice I'm in the sine quadrant, which means sine is going to be positive. So when I use the reference angle to help me get the ratio for the principal angle, I can keep it positive. So my work would say sine of 5 pi over 6 is equal to sine of its reference angle, sine of pi over 6. And I didn't have to make it negative because we are in a quadrant where sine is still positive. And what is sine of pi over 6? If we look at our special triangle, from pi over 6, sine would be opposite over hypotenuse, 1 over 2. So sine of 5 pi over 6 equals a half. Now let me spend just a minute explaining to you this line. I really want to make sure you understand why those sine ratios are equal to each other. Why are we allowed to say that? Well, what would a terminal arm of pi over 6 look like? If I rotated pi over 6 from the positive x-axis, it would take me to this red terminal arm here. This would have a principal angle of pi over 6 and also a reference angle of pi over 6. Since we're in quadrant 1, they're the same. What would you know about where those two terminal arms intersect the unit circle? Let me just draw a circle that I'll estimate has a radius of 1. Okay, let's pretend that circle has a radius of 1. What could you tell me about the y-coordinate of that point and the y-coordinate of that point? Notice they're exactly the same. They would both have the exact same y-coordinate, which means they have the exact same sine ratio. That's why we're allowed to use sine of pi over 6 to get the ratio for sine of 5 pi over 6, because they have the same y-coordinate. And remember the unit circle, the y-coordinate tells us the sine ratio. So hopefully that makes sense to you why sine of 5 pi over 6 and sine of pi over 6 are equal to each other, and why we're allowed to use sine of pi over 6 to get the ratio for sine of 5 pi over 6. Let's try another one. Let's try cosine of 5 pi over 4. So let's start by labeling the angles around our Cartesian grid. And I need to figure out where the principal angle of 5 pi over 4 is going to take my terminal arm. So 5 pi over 4 is past 4 pi over 4, so it's past pi, but it's less than 3 pi over 2. And let me rewrite these angles with denominators of 4 just so you can see that. Pi is 4 pi over 4, and 3 pi over 2 would be 6 pi over 4. So hopefully you can see that 5 pi over 4 is between 4 pi over 4 and 6 pi over 4. So we are in quadrant 3. And exactly right in the middle of quadrant number 3. So I'll draw my terminal arm. That looks like about the middle. I'll label the tip of this with the principal angle, 5 pi over 4. Right? That means that the rotation from positive x to here is 5 pi over 4. I'm also going to need to know the reference angle, the angle between the terminal arm and the closest x-axis. So the angle between 5 pi over 4 and 4 pi over 4 is 1 pi over 4. So I can label my reference angle, beta, as pi over 4. And if you remember your cast rule, I know that in this quadrant, only tan is positive, which means the cosine ratio of 5 pi over 4 is going to be negative. So when I find cosine of 5 pi over 4, I can use cosine of its reference angle, cosine of pi over 4, but I'm going to have to make it negative because I'm in a quadrant where cosine is negative. And cosine of pi over 4, if we look back to your special triangle, cosine from a pi over 4 reference angle would equal adjacent over hypotenuse, 1 over root 2. So negative cos pi over 4 would be negative 1 over root 2. And then let's rationalize this. Let's multiply top and bottom by root 2. And this gives us negative root 2 over root 4, which is just 2. So negative root 2 over 2. Our last one, secant of 3 pi over 4. Secant is a reciprocal trig ratio. The identity for secant x, so secant, I'll just put a reminder up here. Remember, secant of some angle is equal to 1 over cosine of that same angle. That's the reciprocal identity. So if we're trying to evaluate secant of 3 pi over 4, I can evaluate that by doing 1 over cosine of that same angle, 3 pi over 4. So we're going to have to figure out, okay, well, what's cosine of 3 pi over 4? So let me label the angles on the Cartesian grid. Let me draw my terminal arm. So rotating 3 pi over 4, that would be between a half a pi, right? Half pi is 2 pi over 4, and a full pi. Full pi is 4 pi over 4, so 3 pi over 4 is going to be halfway between there, so it's in quadrant 2, right about here. I'll label the principal angle at the tip. So it's 3 pi over 4 from here to here. And I'll label the reference angle between the terminal arm and the closest x-axis. So in here, I'll call it beta. The difference between 1 pi and 3/4 of a pi is 1/4 of a pi, so pi over 4. And based on cast rule, I know in this quadrant only sine is positive, which means my cosine ratio is going to have to be negative. So when I'm evaluating cosine of 3 pi over 4, I can just do negative cosine of its reference angle, pi over 4. And cosine of pi over 4, if you remember your special triangle, cosine of pi over 4, we just did that, is 1 over root 2. So I can replace cosine pi over 4 with 1 over root 2. So I have 1 over negative 1 over root 2. And 1 divided by something just means it's reciprocal. So just flip the denominator and I get negative root 2 over 1, which is just negative root 2. So secant of 3 pi over 4 equals negative root 2. We're almost done. Example 2 says find the value of all 6 trig ratios for 5 pi over 3. So let me start by labeling my angles. And if you can't see that 5 pi over 3 is in quadrant 4, I could rewrite these angles with the denominator of 3. So this would be like 1.5 pi over 3. This is 3 pi over 3. This is 4.5 pi over 3. And this is 6 pi over 3. So 5 pi over 3 is between 4.5 pi over 3 and 6 pi over 3. So if I rotate 5 pi over 3 from the positive x-axis, it brings me to about right here. So I'll label the principal angle, the angle from here to here, at the tip of the terminal arm. So here's 5 pi over 3. The reference angle is the angle between the terminal arm and the closest x-axis. I'll call that angle beta. And to calculate that angle, I would do 6 pi over 3 minus 5 pi over 3. That's 1 pi over 3. And now I can use that reference angle to get me all 6 trig ratios if I remember to consult the cast rule, which tells me in the quadrant that I'm in, cosine is positive, meaning sine and tan are negative. So let me just shrink this diagram a bit so I have room to write all the information I'm going to do for my calculations. Okay, the first of the 6 ratios that I'm going to get is the sine ratio. I'm also going to need to know cos, tan, cosecant, secant, cotangent, but I'll do sine first. So I want sine of the principal angle, 5 pi over 3. So I want sine of 5 pi over 3. I'm allowed to use its reference angle, pi over 3, to get that ratio, as long as I consult cast rule to see if I have to make that ratio positive or negative. And since I'm in the cosine quadrant, I know that only cosine is positive, which means sine is going to have to be negative. So sine of 5 pi over 3 equals the negative of sine of pi over 3. And sine of pi over 3, if we look back to our special triangle, sine from here would be opposite over hypotenuse, root 3 over 2. So sine of 5 pi over 3 would equal negative root 3 over 2. And let me just take 2 seconds and give you another explanation as to why that part of the equation is true. Why is sine of 5 pi over 3 equal to the negative of sine pi over 3? Why does that make sense? Well, if I were to rotate pi over 3, that would bring me to this red terminal arm that has a reference angle and principal angle of pi over 3. And if I were to look at where did those terminal arms intersect the unit circle, let me just draw a unit circle that, let's say, has a radius of 1. Where would they intersect the unit circle? The red one would intersect there, the green one would intersect here. Now notice those don't have the same y coordinates, but they have the same absolute value. This y coordinate would be root 3 over 2. This y-coordinate would be negative root 3 over 2. So because I know they have the same absolute value, but are opposite signs, I can just multiply one of them by negative 1, and then they're now equivalent. Okay, let's get back to actually calculating the 6 ratios. So let's now do cosine of 5 pi over 3. Cosine of 5 pi over 3. I can use its reference angle, and I can actually leave it positive because we are in the cosine quadrant. So that equals cosine of its reference angle. And cosine of pi over 3, if we remember the special triangle, cosine of pi over 3 would be equal to adjacent over hypotenuse, which is a half. And now let's do tan of 5 pi over 3. That would equal negative tan of its reference angle. I had to put a negative because we're in a quadrant where only cosine is positive. So negative tan of its reference angle. And what is tan of pi over 3? Look at the special triangle. Tan from there would be opposite over adjacent, which is just root 3. So I can put negative root 3. So we now have the ratios for sine 5 pi over 3, cos 5 pi over 3, and tan 5 pi over 3. Using those ratios, I could figure out what the reciprocals are. So the reciprocal of sine is called cosecant. So cosecant of 5 pi over 3 is just equal to the reciprocal of the sine ratio. So the reciprocal of negative root 3 over 2 would be negative 2 over root 3. And if we rationalized that, I mean, I'd be fine if you left it like that, but if we rationalized it, multiply top and bottom by root 3, we would get negative 2 root 3 over 3. And the reciprocal of cosine is secant. So secant of 5 pi over 3 is the reciprocal of the cosine ratio of 5 pi over 3. So it's the reciprocal of a half, which is just 2. And cotangent of 5 pi over 3 is equal to the reciprocal of tan of 5 pi over 3. And tan of 5 pi over 3 is negative root 3. The reciprocal of that would be negative 1 over root 3, which if we rationalized would become negative root 3 over 3. Our last example will do a bit of an application question. Justin is flying a kite at the end of a 50-meter string. The sun is directly overhead, and the string makes an angle of pi over 6 with the ground. The wind speed increases, and the kite flies higher until the string makes an angle of pi over 3 with the ground. To determine an exact expression for the horizontal distance between the two positions of the kite along the ground. So the kite started here. The wind came, blew the kite, so it went even higher. It's now up to here. We want to know the difference in the horizontal positions. So the horizontal position at the start would be equal to the x-coordinate of that point. So we'd have to figure out what that is. It looks like it's somewhere between 40 and 50. And then after the wind blew the kite higher, the x-coordinate of that point, it looks like it's 25. I don't know exactly, but we'll have to do a calculation to figure it out. What we want to figure out is how far horizontally did it move? So what we're looking for, what's the difference in those x-coordinates? What's the length of that yellow side I just highlighted? So we could calculate that by doing x-coordinate 1 minus x-coordinate 2. So that's what we're looking for. So I'm going to break this problem into two triangles. So I'm going to call this blue triangle I'm highlighting, I will call this triangle number 1. And if I can find the length of the bottom side of that triangle, that will tell me the x-coordinate of the point. So I need to find the length of that bottom side. I'll call that bottom side x1. So I'm going to redraw that triangle over here. It's just going to be a rough drawing where I know this is x1. I know this angle, the angle it makes with the ground is pi over 6. And I know the length of the kite string is 50 meters. And I know it's a right triangle. And I'm also going to redraw the other triangle. I'll highlight in red. I'm going to need to know the length of the bottom side of that one as well. I'll call that x2 so that I figure out the x-coordinate of the point where the kite is. Let me redraw that triangle. So in this triangle, the bottom side I'm calling x2. I know the length of the kite string is still 50 meters. It's a right triangle, but the angle the kite makes with the ground is now pi over 3. And to figure out the horizontal distance the kite has moved, I'm going to have to figure out the difference between x1 and x2. So I'm going to have to find an exact expression for the length of x1 and x2, because in the question, notice it says determine an exact expression for the horizontal distance between the two positions. So no estimations allowed here, no rounding, we need exact expressions. So let's look at the blue triangle first. Let's get an exact expression for x1. If we look at this triangle, I have a reference angle, and from that reference angle, I want the adjacent side, and I know the hypotenuse. So cosine is going to be helpful for me to get an expression for x1. Cosine of the reference angle would equal adjacent, x1, over the hypotenuse, 50. And then let's isolate x1. So multiply both sides by 50. I get 50 cos pi over 6 equals x1. And cosine of pi over 6, I can get an exact expression for that from my special triangle. Cosine of pi over 6 would equal adjacent over hypotenuse, root 3 over 2. So I can replace cos pi over 6 with root 3 over 2. So I have 50 times root 3 over 2 equals x1. 50 divided by 2 is 25, so I can say x1 equals exactly 25 root 3 meters. Let's do the same thing, but with the red triangle and get an exact expression for x2. So once again, I have my reference angle, adjacent, and hypotenuse, so I'll use cosine again. Cosine of the reference angle pi over 3 equals adjacent, which is x2, divided by hypotenuse, which is 50. Multiply both sides by 50, I get 50 cos pi over 3 equals x2. And then cos pi over 3, let's use our special triangle to get an exact value for that. Cos of pi over 3, adjacent over hypotenuse, is 1 over 2. So I can replace cos pi over 3 with a half. And a half of 50 is 25, so I have x2 equals 25 meters. So the horizontal distance started at 25 root 3 meters, and it finished at 25 meters. So how far did it move horizontally? So I'll say horizontal displacement equals, it would be the difference between those two. It would be x1 minus x2. So 25 root 3 minus 25 meters. That's an exact expression for it. I suppose we could common factor out at 25, or we could just leave it like that in standard form. It's fine like this. So 25 root 3 minus 25 meters is the horizontal displacement of the kite. All right, that's it. Hopefully that was a good review for you about things like unit circles, special triangles, and reference angles. And hopefully you're now comfortable working with those when the angle is in radians.